Hello everyone, I am back after a long hiatus. Today we're creating a simple starter game, a good first experience with Godot, if you already know the basics. We are making something heavily inspired by Fishy, a classic old flash game where you play as a fish. The game has a simple rule. We can eat any smaller fish, but get eaten by any fish larger than us. I am making this with version 4.2.1. The entire project is available on my GitHub. Check out the description down below for that and any further links that I might provide. We will start with a simple blockout and get the logic in place. Then I will draw some very simple fish before we add some finishing touches. This is quite a simple project, written entirely in GDScript. It's going to contain some common use cases that you might expect, such as custom signals, groups, auto-loading, tweening and timers. Let's jump right in and start by creating a 2D scene, since this is a 2D game. Here we are with a completely empty 2D scene. I will save it as main scene. The first thing I will do is create some basic folders, like assets and scenes, to store my data in. Scenes are essentially everything in Godot. In other game engines we have prefabs or blueprints, but in Godot everything is a scene. A scene is a hierarchy, or a collection of nodes. So let's create our player scene. Now we have a scene called player. We can change its type. There are many different types of nodes. What would be the most fitting for our player? Underneath node 2D, we have all 2D related nodes, and collision objects are things that can collide. Our player is going to move and collide with other fish. Now I can choose anything. So for example, maybe I think it will be a sprite sheet to animate the character. That's fine, I can just change it later. We can add new child node. We do this by pressing Ctrl+A, or hit the little plus icon in the top left here. The base node of all 2D sprite-based nodes is the node 2D. I can add, remove, or change the type of nodes here at my leisure. If we just want to add a sprite, then we can add the sprite to display our player. But since I don't have any art yet, we can call it temp image and use the Godot icon. This is a classic. Our beautiful robot mascot is the perfect placeholder. So now our player is mainly a sprite sheet, with an empty 2D node and a sprite. It cannot collide yet. This isn't really what we want, but I also want to show that it's not a problem. Let's start correcting this. Let's add a collision node, so that we can collide with things, such as collision shape. We can select the shape. In this case, a rectangle seems reasonable. But now it's giving me a warning. It's a derived node, and has to be a child of either a static body, character body, or an area. So it's telling us how to use it. Let's change the type of our node to character body 2D. Or I could also add it and then change it to be root afterwards. We can right-click the character and make scene root to make it our root. We now have a character controller with a sprite attached. Now we have a character controller, a sprite and a collision shape. Let's call the root player. Let's call the root player. Now I'm not sure if I will use these or other sprites yet. That's fine. Let's keep it but hide it. The collision shape now belongs to the character body 2D node. It represents the shape of that node. So let's write our first piece of code. Let's code how this player will work. To many, this is a scary part, but once you get to know it, scripting is really the fun part. This is where the magic happens, and everything comes to life. Let's create a new script. Now, C# as a language is nice, but I will write everything in GDScript. Let's just call this player movement. I can then drag this script onto the player. There is also an add script button at the top to create and attach a new script directly. Clicking the script icon opens the script if one is attached. You can also just switch to the scripts tab and select it there. In here we have two pre-written functions, ready and process. Ready happens once on startup, when the node becomes active, and can be used as an entry point or to set values right at the start. Process happens every frame, hence it has the delta parameter. Delta is the time that has passed since the last frame. We want our player to move. The code will contain the logic for moving the player, but to connect the input from our player in Godot into our script and use it, we first need to read that input, which means we need some input. So before we get to the code, let's open project settings, switch to the input map tab, and there are multiple tabs here, one of which is auto-load, which we'll get to later. In the input map, we can create actions and bind them to some input, like the keyboard. I want to be able to use the WASD keys to move. I know the original Fishy only allowed for the arrow keys, so why don't we use both? Simply write the name of the action and all actions that have to be done one by one. Let's create one called move up, then move down, move left, and move right. And over to the right here we have a small plus sign. Click it to configure the action. You can look through the menus here and find the input you want, or simply click the button you want to use, and Godot will detect it automatically. So I can just click the up arrow on the keyboard and hit OK. Let's add an alternative by clicking W, and now both of these keys can trigger this action. Let's do this for the rest of our actions as well. These are all of the controls for this entire game, at least until you remake it. So in this code we now want to read from this input. I'm assuming you know at least a little coding here. Otherwise, in the description will be a link to the Godot coding docs. Var creates a new variable. Let's call it input. Input.getVector will create a new vector. And we can see our actions here, and we can just select them from this list. Typically, you want to normalize vectors like this, so that it always has a length of 1. But Godot actually auto-normalizes this for us, with the input.getVector call, so we don't have to. Since its length is always 1, that means that we will move really slowly. It will move us at a speed of 1. Let's increase this vector with a new variable that we'll call moveSpeed. I will set it to some value like 100 to start us off. Next, we will want to apply this movement to something, and we are of type character body 2D. Let's make a reference to our character body 2D part by using an exported variable. The export annotation will make it visible in the inspector. We can now choose our own character body 2D, and this will help us autocomplete some of our code. Now we can go playerBody.velocity. Oh hey look, it helped me autocomplete. Now that it knows that it's a character body 2D, it knows of the velocity. Let's set this to our input, which is our direction, and multiply it with the move speed. Now we have applied the values to our body. Now we need to tell it to update. We do this by writing playerBody.move and slide. Let's go back to the main scene and drag our new player scene into it. The player is now part of this scene. This small purple bluish outline represents the camera viewpoint, and if I hit play, we can see the player up in that corner, and it now moves. First we set the values and then we told the body to use them. We can move up, down, left, right, and always with constant speed. Let's have a look again. A reference to the character body, which we don't really need, but we'll need it later. I'll come back to that. We have a move speed value that we can change at any time. We read the player's input and use that as a direction. We set our velocity to that direction times the speed and apply it to the character. It's short and simple. In GDScript, an empty function must have this pass keyword. It can't just be empty. Pass just means we ignore everything that comes after it. Our empty ready function must have this until we have some logic to put there, but we can safely remove it from the processor. Back in the scene, let's center our player to the camera. I also increased the speed a bit. Now we're super fast. Okay, let's create a new scene for our enemies. There are only two things in this game. The player, which is a fish, and all of the other fish. Let's call this scene Fish. We might have to change that later, but now that's not a problem. So we want to create the enemy fish now. We want to be able to see it first of all, so let's add a sprite, just like we did for ourselves. Now to differentiate between them, I will change the color to be slightly red. You do this through the self-modulate option. So what does the enemy actually need to do? Well, mainly it needs to collide with us, the player. So what should this node be? Should it also be a character? Characters move. Static bodies and statics don't move. Possibly we want a character, but we don't want them to stop each other. Let's try using an area 2D. An area 2D is essentially a trigger, so the enemy fish is a trigger area that the player enters, so it won't stop us like a physical object would. We could do this in a bunch of different ways. Let's try and see if this works. When I do, it gives me a notification that the area lacks a collision shape. This may seem odd if you're not used to it. The area is its own node, and it needs a collider attached. So let's hit Ctrl+A to add a collision shape 2D. A rectangle makes sense right now, just like it did for the player. So let's stretch that out to cover the entire sprite. What is the area for if the collider does the actual colliding? Well, the area 2D uses the collider and has signals such as the body entered signal. This can trigger events or alert other actors and nodes when they hit this area. Now we have our enemy. They act as a trigger for the player. We just haven't connected the area to it. Before we complete this, if we look back to Fishy for just a second and what we are looking to create, all fish are very similar. They all move, both the player and the enemy. They all have a size. They all interact with the player. So as soon as we write this collision logic, we are saying that two fish have collided. All fish can collide, they all have a speed, etc. We should collect all of these properties, all of this data, and determine how it's going to be used first before we get to the logic. And since this is a small project with a few similar classes, we will make use of inheritance. If you know any programming, you know inheritance. The player is a fish and the enemy is a fish. So let's have a base fish class. Let's create another folder and call it scripts. Here we will place all the other scripts that don't belong to any particular scene. Typically, there are two ways to order your folders and your workspace. In tutorials like this one, you will typically see an assets folder, a scripts folder, and an art folder, etc. This is because the scope of the project is typically small, and so it's what most people do. In larger projects though, you tend to want everything related to be together. It doesn't make sense to have the player art in one folder, the player code in another, and to have everything spread out like that. A player in a larger game might have tens or even hundreds of parts and components. You have tens of different enemies, all with their various components. You want them all together somewhere where it makes sense. So you order your folders, you create a player folder, and anything related to the player specifically is put into that folder. Same with your enemies and everything else. Now I'm mentioning this because I'm doing a bit of both here. Scripts that aren't directly used by something can be placed in the scripts folder, but the player movement script might as well be placed into a player folder together with the other data related to the player. Anyway, let's create script fish. It's going to be a superclass or a base class, however you want to call it, that the player and the enemy can inherit properties from. Although this file is called fishgd, the class doesn't actually have a name yet. Let's give it one and call it fish. Let's add a variable and call it size. I don't want to deal with fractions here, so I'll just cast it as an integer. All fish will have a size, so we can compare them to each other. Our player right now extends node, which doesn't help us very much. Let's change that to inherit from fish. Now we can use the size variable in fish. Let's do that now and just initiate that size to something, like maybe 5. Before I did this, we were working on the enemy fish, so let's go back there and finally add a script to it. And I think I'm going to call this enemy fish, since fish is already being used. And let's have it inherit from fish. Let's name this enemy fish, because the scene is called fish. It extends fish. Everything is just fish right now. It's already getting confusing, so let's refer to this as enemy fish. The enemy is going to move, so it's going to need a move speed. We can see that the player has one, so clearly that's something that we can move from the player to the fish class. It's a shared variable. Largely the reason we want to store as much in fish as possible is to just not duplicate things unnecessarily. Let's write it once and have it work twice. This is more powerful, but it's also less prone to bugs than if we make changes later, and we need to change it both in the player and in the enemy class. Now I'm going to add some more data to the enemy, and if we notice later that we also need this for the player, then we will just move it to the fish class. I want the fish to start off screen, so I need to know its starting position, and I want them to move across the screen from left to right, or vice versa, so they need a direction. I want the fish to do a bunch of stuff, like spawn on the sides, have random size, move across the screen, etc. Let's write a little step-by-step instructions for ourselves here. It can be helpful. I want it in the ready function, because as soon as the fish spawns, this should be done right away. We want a random fish size, we want a random starting position, and we want a direction based on where we started. We also want to change the fish scale to fit the size. So what should happen in the process function? What should happen every frame? Well, we just want to move, right? So add movement over time. The player also has a direction. You might have already noticed. So let's drag that back into the fish class and then use it on our player as well. Now back in the main scene, let's drag in the enemy fish to test it out. I can start the game. I can move, although I'm slow again, and I can move into the enemy, which is a trigger, but it doesn't do anything yet. Back in the enemy fish scene, I briefly showed this signal, body entered. We will now hook up this signal to the enemy fish class. So when a body, our player, enters the trigger, we can perform some action on the enemy fish class. I haven't really explained signals yet. Just think of them as events, and we are using the observer pattern. The area starts an event, and anything that is listening will be informed when that event is triggered. In this case, it's going to call this onBodyEntered function. You can see this green little symbol, which shows that this is called through a signal. To test this out, when something enters the area trigger, we could print a message. If I test this out, you see down here in the console that our message was printed. The body parameter here is just whatever enters the trigger. Now we know that the player is a fish, so we can cast this as a fish. It's not just something, it's the player. And we know for a fact that the player is a fish. Now we are ready to write the main logic of the game. If the body size is larger than our size, then do something. Else, if we are bigger, then we just perform some other action. Now we have to set the sizes. So in the fish script, we added the export annotation to size, which lets us manipulate it through the editor. Just temporarily, I can now see and set the size of any fish through the inspector. Our player can have a size of 10, one enemy is 5, and the other is 20. As we enter the first fish, it prints, "Oops, player is big," and the other fish prints, "I am bigger." I also just noticed that the fish inherits from node. Now the plain white node doesn't really have much use. It exists in the scene, but it doesn't have a transform or anything like that, which makes it a poor choice to inherit from if we want things to move around the scene. Let's just make it a 2D node for now. This means that our enemy fish now has a position that we can manipulate. Let's add the direction and the move speed in the process function onto the enemy. This happens every frame, and voila, it just works right away. I also changed so the enemy or the player will be removed from the game depending on who is bigger. This is done using the queueFree function. It will remove the object at the end of the frame when it's safe to do so. To recap, all fish are now inheriting from node 2D. This lets us manipulate their positions in the scene. I suggest starting with the base node, like node 2D, and changing it later if you find some other node that would be better. This node is suited to being moved and updated, so it fits our purpose rather well. Let's clean up after ourselves a little, and also come to think of it, the starting positions will be needed by the player also, because we want them to start in the center of the scene every time. So let's move that to the fish script. Now we have a working enemy fish. The collision logic is working, and our player can move, but we need some way to automatically spawn new fish over time. We're not gonna hand place all the enemy fish. We also want them moving across the screen. If they are on the left, they should move to the right, and vice versa if they're on the right. This will be a lot more code than we want to place on the enemy fish start function. Let's create a spawner to take care of it for us. This is also a generic script that doesn't really belong to anything else, so I will put it in the scripts folder. It's inheriting from node since it won't move. Let's call it fish spawner. I wrote a few different versions of this and just kept going back and forth with how it should work. The recording got a little messy. Let's walk through it and discuss what it does and how it works. So let's write down our goals. First, we know we want a function to spawn a new fish. This needs to happen repeatedly while the game is running, so we need to call the spawn function in the process function. But we don't want it spawning a fish every frame, that would get crazy. So we'll control the flow of enemy fish using a spawn rate variable. Next, just spawning the fish in the scene isn't enough. We need to initialize and set some values on the fish. We need to randomize their position, their size and speed, etc. The initFish function will take a class fish as an argument and work to change its values. So to spawn a fish, we need a reference to the enemy scene. At the very top, we see a constant. This is us preloading the enemy fish asset to use it as a template to spawn more of it. We are just pointing to the enemy fish resource so we can spawn more of it later. The 1 on spawn rate is going to mean 1 per second. Instantiating the fish is as easy as calling instantiate on it and adding that new fish we just instantiated as a child. This is a standard way of spawning something into your scene. Next, we'll just call the initFish function on that fish we just spawned to set its values, and that should be it for the spawning part. But none of this will happen right now. We're never calling spawnFish. Let's do that in the process function. But like this, it's going to happen every frame, like I mentioned before. Therefore, we're going to use the spawn rate like this. This is the easiest kind of repeating timer you can probably make. If the timer reaches below 0, we spawn a fish and reset the timer to 1. Otherwise, every frame reduce the timer by delta. This is the time that has passed since the last frame. So we're just counting down from 1 until we reach 0. With the spawning done, let's take a closer look at the init fish, which is going to be the somewhat longer part here. The fish are now instantiated into the scene, but they won't do anything. They will just sit there. We want fish to spawn on either side of the screen, so let's do two things. Let's randomize an integer between 0 and 1. I know it says 0 and 2. The first value is inclusive and the second is exclusive. We also create a start position where the fish will be moved to. We will calculate that next. Let's do x and y separately. Starting with the horizontal, x. If the random side was randomized to 0, let's just say that means the left side. And if it's 1, that means the right side. It's going to look something like this. So on the left side, we set the position to -200. That just means 200 pixels to the left of the screen. And we set the fish direction to point to the right. That's positive on the x-axis. Otherwise, the fish will spawn on the right side, we add 200 to the screen width and set the direction to look to the left, negative x-axis. After this, I'm going to change the size of the screen. I am thinking 920 by 1080p will be good, we'll see. So let's get to the Y value. Now, since we don't need to check which side or anything, it's as simple as randomizing between two values. I want them inside the screen here, so I will reduce the number a bit rather than increase like we did before. Let's just try some values like this and see how it looks. Next, we'll set the Y component of the start position to this value. Simple. Both the horizontal, X, and the vertical, Y, have been set on our new start position for the fish. Now let's set the fish position to this new start position that we have created, and that should be it. Lastly, I'll set the move speed to some value, or they won't move, but we'll change that later so that the enemy fish can set its own value. So with the spawner in place, fish are now spawning on either side of the screen. They are swimming from side to side, and we can collide with them. Good job so far. Let's list some of the work we still have to do. The most obvious is graphics. This is looking incredibly boring right now. The second is that the fish never despawn. You can't tell just from looking at it, but they keep swimming forever. Sizes are not randomized, and it's only a value still. It doesn't affect our actual scale yet. We won't fiddle with that until we have the sprites in place though. Another is with the settings. You see, to have the fish spawn on either side, we hard-coded where they would spawn. This means that the resolution has to remain the same. We also need to make sure that changing the window size won't affect the size of the play area. Otherwise, fish might start to spawn where we can see them, and other weird issues might arise. Here are the settings we're using. Resolution is set to 920 by 1080p. Now, my monitors are 1440p, but I realize 1080 is more common, so it could look better by setting a higher target resolution. Stretch mode is set to viewport. Aspect is set to keep. This means that the window can be changed, but the scene will remain the same. Resolution changes when changing the size of the window, so it will fit your screen. There's a lot to read on this, and I will add a link to screen resolutions from the official Godot document. But now we can resize the window however we want, and it should work just fine. Just remember that if you change the target resolution in the settings, you may also have to change these numbers in the spawner. The player can swim outside of the scene. The camera is statically just showing this one area, and there is nothing stopping us from also swimming indefinitely in any direction. This is actually quite an easy fix. Because the camera doesn't move, and we know the size of the camera window and where the edges of the screen are, we can just not allow our player to move outside those bounds. Let's declare the bounds of the screen and test that we can track where the player is through code. If our position is ever less than 0 on either X or Y, or if it's larger than the edge of screen values, then we print a message. Indeed, whichever edge we approach, we can see the message. So this is fixable through code. Now I'm going to remove this because I don't like how that looks. Instead, I'm actually going to clamp the actual values off our position. So instead we go position.x clamp to 0 or the edge of screen. And position Y gets clamped between 0 and the edge of the screen. Voila, that should do it. And look, I am now bound to the window. We are calculating from the center of our sprite, so of course, half our sprite goes through the window. You can add some padding, but this is fine. We can never go outside. There should be no glitch that pushes us outside the bounds, because our actual coordinates in the scene are clamped to never go beyond these values that we have set. Now we need to do kind of the same thing for the enemies, but instead of clamping, we will remove them once they roam outside of the screen. Let's create a new variable, distance traveled, to keep track of how the enemies have moved. Enemies spawn on one side of the screen. We know it's 1920 pixels wide, so we can estimate how far they need to move before reaching the other side. Every frame we will add to this distance traveled. We are now tracking, or counting, how far we have moved every frame. And if we have moved further than some distance, let's write 500 here temporarily, then we remove the fish using q_free. And oh, typo here. Distance traveled is the length of our direction times move speed. Direction is a vector too. We can't add that to an integer. Let's also make sure that the distance traveled is a float. We don't want it to be an integer that only counts whole numbers. So why did I make the value 500? Well, so that we can see what is happening. Now we see it working and can confirm that it works. The fish move 500 pixels and then delete themselves. That's what we want. Now we just have to adjust that value of 500. Let's create a new variable called distance to end. and set it to the width of the screen 1920. This won't be enough, but it's close. Let's add some padding. If you remember when we first spawned the fish, we created an initial offset of 200, so fish would spawn 200 pixels outside the screen. Well, let's use that same idea here, but with a larger value. I had to start using smaller values, because now that it works, we can't tell if it works or not. We just see the fish swimming past. Thanks to some testing, we know that this is working. The fish are despawning after reaching the other side. Now let's start randomizing the size of the enemy fish. Let me explain how I want this to work. Each fish has a value associated with it. Let's say a value between 1 and 100. The scale of our fish is affected by this value, so we get bigger or smaller. This way we can compare fish against their size value, instead of trying to compare the scale of their sprites. So if I add a line to just randomize the size on startup and then play. Before, all fish were the same and smaller than the player. But now they can be both. But I still can't see what size they are. Before we mess with scale, there's another way to see what size they are, and that is simply to display it. Maybe that's not something we want in the game later, but it can be useful for debugging. Enter the enemy scene, add a new label node. Click on Label Settings, New Label Settings. I will increase the font size a bit, add a slight outline and center it underneath the enemy, using anchors and just dragging it to the middle. In the fish script, since these values are now randomized or otherwise set on startup, they no longer need to be using the export annotation. That was just so we could manually set their values. Although I will keep move speed exported, as the player uses that. We also need to be able to change the text on our new label. Both player and enemy fish could do this. So let's just add the label here. I will just call this label text. Which is a stupid name for it, I will admit. Now we can assign the text label in the inspector and select the new label node we added. And in the spawner script where fish have their values randomized, we will set the text of that label to the size that we just randomized. To cast the integer size to a string, we use str, not string and not toString. And hey look, now we can see the enemy sizes. Back in the player scene we also have a label node, but we aren't using it yet. I'm going to add a label here, just the same as we did before. I just realized I also want the enemy speed to be random. Let's quickly add that, just the same way that we randomized the size. Right now, the enemy handles collision with the player, so the logic goes here. If we are displaying sizes now, we might as well increase the player size and display it while we're at it. I'm going to increase the player starting size to 25, just so we don't have to be afraid of most all other fish while we're just playing with the mechanics. Okay, here we go. Right away we can tell I forgot to display the player starting value, so it just reads 0. But we know it's 25. The enemies now move at random speeds, some fast, some slow, and we can see their sizes. And now we've grown by 1, and we can see it on the label. All in all, we're almost done with the main mechanics. Let's quickly adjust so we can see our size right at the start by adding it to our ready function. Now I'm just going to zoom past the drawing part here, because I realize I'm not the right person to try and teach you this. I can do some pixel art, I can do some 3D, but I can't draw. I'm using Krita. I'm using shapes and Bezier curves to get the rough shape and then color it. I suggest looking at drawing tutorials specifically, if you want to get better at it. I'll finish this up, and then we can get back to where we belong, in Godot. Dragging the new fish into our enemy scene to start. You can tell it's a whole lot bigger than our previous image, and we have some adjusting to do. I drew 2 different colors of fish, one for the player and one for everything else. Let's remove this modulate option I set at the start, and have the enemy fish just be green. I also imported the player fish as orange. And, oh, hello. Yeah, we have some adjusting to do. Let's just scale down the sprite, way down, to fit the collider we have. We could also change the scene to instead fit our new sprites, but this is the easiest option. I am scaling the sprite, not the entire player object. That's important. That's what we will do through code. We are getting tired of this gray background as well. Let's drag in a sprite and call it background. We will use a built-in texture here, a gradient. I will change its color to be different hues of blue, like water, and just drag and scale that background to fit the entire scene. I also need to rotate it to make the darker part be at the bottom. Hey, it already looks much nicer, despite my terrible drawing and a simple gradient background. Okay, now let's get to the scaling. Finally, geez. The eating logic is still on the enemy. When we collide with the player, we refer to them as body. Let's change that to player, because that is in fact the only thing that we are colliding with. Instead of changing the player size, the player could change and be responsible over their own size. Let's head back to the player and make a function here called grow. In the enemy script, we call the grow function on the player, and we move the growing logic back to the player. Just like before, we need to increase our size by 1, and we need to set the text to display our new size. However, that's not all. Although we have this internal number to represent our size, the actual scale in the scene needs to be different. I have scaled the sprite down to 0.08, which looks reasonably small. Let's introduce 2 new values: the actual scale value we want to change, and how much it should increase after eating a fish. We need a small fixed value to add to our scale whenever we eat a fish. Let's call it growth per fish. To start off, I am setting this to 0.01. That would mean that eating 100 fish would have increased our original scale by 1. We start the scale at 0.08. And this next line does a few things. We set the fish scale to the smallest of 2 numbers. Fish scale plus growth per fish will give us 0.09 after eating our first fish. We choose the smallest of 0.09 and 1, which will of course be 0.09. The next time we grow, our scale will be 0.1, followed by 0.11, and so on, until we finally reach a size of 1. Then this function will always return 1, so we can never grow beyond a scale of 1, so it also clamps the value. Next, we set our actual scale to be this new scale value, represented as a vector 2, and later on we will want to create a small effect or animation here. Now we can eat other fish, and we grow a little each time. Now the next issue is all fish are pointed the same way. Luckily, there is a simple fix. The sprite node has a flip option, one for horizontal and one for vertical. By just flipping this value, we change which way the sprite is looking. I am adding an exported variable to a sprite in the fish script, since all fish have a sprite. And then I add a new function called turn. This will set the direction of the sprite to be the same as the direction we are traveling in. In the player's process function, we can now call this turn function. So every frame, the sprite is turned to look the way that we are pressing on the keyboard. The reason the code looks like this, and is an ugly if-else case, is because if the direction value is 0, we aren't looking for it. We only turn if the direction is either above or below 0. Why is that? Well, if the direction is 0, that means we have let go of the keys. And if we let go of the keys, then we don't want to change anything. And on the enemy fish, since direction is decided in the ready function and they never change it again, we can just call turn here. Alright, next problem. This isn't really a problem though. You see, a good habit to get into is not to add everything to a scene beforehand, but rather spawn it in when the game starts. I don't mean backgrounds and stuff, but objects like the player. Just like we want our enemies to spawn over time, we might also like the player to be spawned in through the spawner. A direct reason for this would be if we want to reset the scene later back to its default. If everything was spawned and kept track of, we can easily do it again to respawn everything without reloading the scene. Reloading the scene might remove the player's score or change other things that we don't want. It's not happening here in this game, but like I said, it's a good habit. All we have to do is add the player to the fish spawner. We already have the enemy fish scene preloaded in the spawner. Now we add the player. The player spawns at the start, so let's make a ready function and instantiate the player fish each time the game starts. And also let's set their starting position to be right in the center. Actually, let's move this to a separate function called spawnPlayer to make it extra clear. So now I can remove the player from the scene. Now it's just a background and a spawner. Yet, when I play, everything works the same. Okay, whew. After all this work, let's play a little. Let's export the spawn rate value so we can change it in the inspector. I will set it to 0.1 instead of 1. Yeah, that's way more fair. Let's try 0.01. Now there's a wall of... This actually reveals 2 things to us. 1, performance is not an issue. 2, I set the Y values wrong in the spawner. As we can see, they don't spawn at the bottom. And 3, there is no maximum number of fish. If we imagine the fish were more expensive to render, we might need a maximum number just in case, so it doesn't lag or crash. First, let's fix the Y value discrepancy. The window is 1080p tall, We want to spawn inside the window, so we'll do a 20 pixel padding and spawn between 20 and 1060. Now we get fish even at the bottom. Next, the max amount of fish. There is actually a neat way to track how many enemies we have in the scene without counting them ourselves. Let's add the enemy fish to a group. If I click on the enemy fish and look over here next to the inspector window, this is where we have all the signals of this node, but also groups. So let's add the enemy fish group. There is now a group for our enemies. If we look here, we can see that the root enemy is in this group. Groups do a lot of good in Godot. It's a powerful and flexible feature that lets us organize our nodes. If all enemies are in a group, instead of accessing each enemy for something, we can query the entire group. When we collide with something, we can ask what group it belongs to. We can also send signals to the entire group, etc. Now in the spawner, instead of just checking the time that has passed, we will add this line: get tree, get nodes in group, enemy fish, dot size, and compare that to the max fish count. So this line will now return how many fish are active in that group, doing the counting for us. And we can just ensure that it has to be below the maximum before we allow a new fish to spawn. We'll have the enemy initiate their own values instead of the spawner as much as possible. I'll just copy paste these values from the spawner script into the enemy fish script. Now we can see that a large clump of fish are spawned right at the start, but then it slows down, because a fish has to disappear before a new one can spawn. If we eat a lot of fish at the same time, a large wave of new fish would spawn right away, because the timer is set so low, but so is the max allowed number of fish. Let's also export that max value, so it's easy to play around with in the editor. Now that we have seen how powerful groups can be, let's also add the player to a group. This allows us to sort of anonymously ask if something is a player, by checking if it's in that group. So in the enemy script, when colliding, before we assumed it was a player, but now we can easily check if it belongs to the player group, and if it isn't, we simply return out and ignore it. Now, while we're in the enemy script, let's get to something super important that you've probably been waiting for, and that's scaling the enemies. So far, we've only scaled ourselves. I'm just going to paste in the same code that we used for the player, except now we're doing it on startup, where we initialize the enemy fish. But now I'm doing something stupid. I'm copying and hard coding values. This breaks the drive principle, among other things. We want the enemy to scale exactly like the player. If I later change that logic on the player, it won't be reflected in the enemies, and vice versa. We are setting ourselves up for a headache. The solution is to create a manager script that calculates what size a fish should be. Let's create a new script in the scripts folder called size manager. And now we will also touch upon something that I mentioned in the beginning of this video, and that is the autoload setting. What is an autoloader? An autoloader is Godot's built-in singleton system. It allows you to define scripts that are always loaded and accessible from any part of your project, just like a static singleton. It's always loaded, it's accessible from anywhere and from anything that exists in the scene. Another fantastic feature from Godot. So what will this size manager do? Well, what if a fish calls to it with its current size, and the size manager calculates and returns the scale that we should be? Let's call this function determine size. In the enemy fish, we call size manager.determine size, and we want to set our scale to whatever value it returns, and we send our size as an argument. Size is always an integer, to keep it simple. Let's cast it as an integer just to be sure. And since we're working in 2D, our scaling is 2D, so let's have this function return a vector 2. Let's decide that no fish can be larger than some value, let's say 5. And that means their scale cannot be above 5. We could make this a constant. So let's start working on this conversion. Let's make a new variable called new size, because we want to return a new size. Just as we have a maximum size, we could have a minimum size. Now we have essentially a minimum and maximum bounds. We can interpolate between these two values, so get this. We want to retrieve a value between the minimum and the maximum, and we input fish size divided by 100. My thought here is that let's say our size is 50. Divided by 100, that's 0.5, and a scale of 1 would be the final size. We need to cast all these values as floats, otherwise the division won't work properly. Now I have applied this to the enemy fish only. Let's see what happens. Well, it works, but it needs some tweaking. And we, the player, are really kinda tiny. Let's now make use of the size manager at the player start function. Let's also update the grow function to make use of that. Now we're starting out at size 5. And we really are tiny starting out. It's a challenge here just finding an enemy that we could actually eat. Okay, biggest problem now is that it's completely random. So the odds of an enemy spawning that are actually smaller than 5 seems, well, small. I have an idea. Let's have the spawner know of the player's current size. And instead of completely random, we create fish that are within a range around our size. So whenever a fish is spawned, we take reference of the player and we send the player scale to the new fish that is spawning. And in the enemy fish, we receive the player size as an argument. Instead of completely random, we use that as the maximum bounds. Wait, no, that won't work. We'll have to be a little more specific. We want the fish to be around our size, but never below some minimum or some maximum value. This may never be below 0, so let's clamp here. It may also never be above max allowed fish size, so let's clamp the maximum as well, which we'll say is 99. Oh yeah, look here. This is easy mode. They are all within our range now. If I speed this up a bit, you'll notice them growing bigger and bigger, just like we are. But hard coding 99 here is actually a bad idea. Let's make it a bit more central. In the size manager, we'll set a maximum size. Let's try 200. And we just call that in the enemy fish. Another thing I want to add before we try again is something really important. I never animated the fish. I just drew a boring old fish sprite. Luckily, we can do a bit of fake animation right here in the code. So I'm thinking that when the player grows, they do a little growing animation. Let's create a new tween and have it affect the player's scale, so we affect ourselves. The property will be scale that we want to change. Scale is a vector too, so let's tween our scale up to 1.1 for just half a second. But then we want to scale down again, so let's do the same thing again, but back to our previous value. Now hang on, the player is in scale 1. The whole point of the game is to change our scale. We need to first determine what our current scale is, and then change it from there. So let me quickly move things around here. We create a new temporary variable to determine the scale that we want to be after eating this fish. We then scale ourselves to that plus 0.1 before going back to the scale we are supposed to be. I'll show you how this looks in a second. But while we're doing this, I just saw another thing that I don't like. The enemy kills the player, but we need to show like a game over screen and stuff, so the player should take care of their own death. Instead, the enemy fish will call die on player. So how will the player trigger a game over scene to be created? Well, let's take advantage of Godot's signals and create our very own. Let's make a signal called player died. You can see here that this signal exists. We emit this signal in the die function. Let's temporarily also turn ourselves invisible and turn off our process function so we cannot move or do anything. While we're at this, the spawner could stop spawning fish to connect to this signal that the player is sending. This part can be confusing, but we can connect to the signal itself. Now, if you Google, you'll find lots of older results where you connect differently, but this is how you do it. Let's have this signal trigger our disable spawning function. Right now, it just prints a message. And there you see, it worked. Instead of printing a message though, we will pass our process function, which will effectively stop our spawning. Now let's try to die. And hey look, no more fish. Logically, if the player can turn itself off, it might need a way to turn itself on again. We will just reload the scene later to restart. But let's make this just in case. It's just as easy anyway. Let's create a start function. It does pretty much the same as our ready function, so let's call it from there. It starts our player and ensures that we are active. Now we can both die and start again. Now let's create that game over scene. We will call it just that. Let's add a control node this time. 2D nodes are mainly for gameplay elements. 3D are of course for 3D, and control are for UI. So we want a panel as a background, and our parent to add our buttons and text to. I will center it and stretch it out a bit. Next we create a label. A label is just text to display. Let's write game over. I will duplicate this in case we want some more text. And lastly, a button, also a control node. This will be a restart button. Most nodes in Godot have their own unique signals, and you can see here that the button has a signal for when it's being pressed. This scene will need a script for us to call. But we also need a manager to handle scene transitions and scene resetting, etc. Let's write a manager now and add it as an auto load so it's available from everywhere. Next, we create the scene script here, game over script. Now the button pressed signal will call the game over script. Just as we've seen before, Godot now creates a function here for the button to trigger. And what do we want to do here? Well, we just want to call the manager we just created to have it reset the game for us. We could call this reset game, and the button calls that. Now the manager needs to know our current scene. I will drag it in here as a preload. We could just as well reload the current scene. Let's try both approaches actually. A reset game function could reload the current scene, and the game over function could load a certain preloaded scene. This might not necessarily be the current one, but perhaps a different menu or a different level. In the die function, we call game over. Short side note, for this menu to appear and be shown on top of all the other stuff, its C index needs to be higher than those other objects. Now when I die, it looks like this. But oh hey, look, a bug. It doesn't disappear after it's been clicked. We can keep clicking the button, so let's just have the menu remove itself upon use as well. Here we are, almost done. It's really starting to come together. I will do a quick cleanup of the project. We've just been implementing feature after feature almost without pause. A neat thing that you can do is color your folders. So I'll make assets red, scenes green, and scripts blue. This helps us visually. Move the sprites into an art folder. The player could get its own folder, like we discussed in the beginning. You can sort your folders however you like, but as the project gets bigger, you likely want to group related objects together. Same for the enemy. I accidentally used snake case here. Being used to C#, I have to force myself to write in snake case, so I sometimes overdo it accidentally. Reading through some of the code, I also just realized that we are performing physics actions here in the player. Dealing with velocity and calling the character body to move. That should be done in step with the physics engine. I'll just remake this entire process function into a physics process, since most of this is related to movement anyway. Now let's give us a way to remove all the labels underneath the fish that show the numbers. We can keep them, but we don't want our players to see them. That would be cheating, and it looks bad to boot. Let's create kind of a debug mode that we can turn on or off that will determine if the numbers show or not. In the fish script, we check if it's on or off and set the visibility of the text. Simple, except there's an issue. You see, the ready function is used on the player. And without going too specific, if the player has a ready function, then that will override the ready function on the inherited fish script. So we need to make sure that the fish class ready function gets called. We do this by just adding this line here. Super. Now let's turn the debug off. And hey, now we just see the fish. At any point we can select the player or the enemy and turn their debug modes on. Okay, one last thing, again. So I just played Fishy to compare, and it struck me that the movement in that game is way more floaty, more sliding. Makes it more difficult by comparison. I have now made this really easy to play with pixel perfect movement and fish that only spawn around their own size. Let's try to add some more drifty, slidey movements and see how that feels. We can no longer set our velocity to just be input times speed. Let's add a new variable called acceleration and set that to some value, and another variable to track our theoretical velocity and later apply that to our player. Velocity will be a vector too, since we have both x and y to worry about. Now if the direction is 0, that means that the player isn't trying to move. Then we should slow down. So the velocity should move towards 0. It should slow down by acceleration. Now, we could create an acceleration and a deceleration if we want different values. I don't think that's necessary, so instead of an instant stop, when we let go of the keyboard, the velocity will slowly drop towards 0. Otherwise, if we are trying to move, it should move towards direction times move speed just as before, but it should kinda increase towards that by acceleration over time. Now we set our player body velocity to this new velocity value, and yes, velocity does conflict with any built-in velocity value, so I will rename it to fish velocity in just a second here. I will start with acceleration at 500. Now we're sliding along the screen. I'm not sure how it looks on the recording, but it definitely feels very slidey. Since this just turned into such a big chunk of code, I will extract it into its own function called movePlayer. Add some comments and tidy up a bit. Okay, now we're done. I'm not gonna add any more things. I think this works fairly well. I am satisfied with the result. We are going to change the MipMap settings to make the textures not look so crunchy. But apart from that, what is left for you to add? You can use this however you like. The source code is available for you to do whatever you like with. Obviously, for it to be a game, there needs to be two things. A fail condition, as in dying. It's only a game if the player can win, right? I never added a victory screen, only a death screen. So if you want to add more to this, finish it by adding a victory screen. It's up to you to finish it. Some other things that immediately come to mind would be for smaller fish to give less size than big ones. We could also show the player just how many fish they've eaten. A background image, animated fish, dynamic bubbles that spawn when the fish breathe, unique fish enemies, etc. You may notice that the textures look a bit crunchy. This is a side effect from us scaling down our sprites, and the rendering settings not being the same as my monitor. To help with this, we can make use of MipMaps. MipMaps help downscale textures to look better far away or when they are scaled down. To activate this, we need to change this setting under rendering, textures, default texture filter. Change this to linear MipMap. Now the project is set to use MipMap. To actually generate them for our fish texture, select the imported texture, switch tab from scene to import, and check the MipMaps generate toggle. Now it looks smoother. And that's it. Thank you so much for watching. I hope you can use this or that it helps you in any way. I will be back with more future Godot content.